Bismillahirrahmanirrahim.
My dear student, I am Dr. Muhammad Yasin. It is our third lecture on pericyclic reaction. Today we are going to discuss the different types of the pericyclic reaction. We will definitely study the electrocyclic reactions, which are also called the ring opening or ring closing reactions. We will discuss the cyclo-addition reactions, and we will discuss the sigmatropic rearrangement, and finally we will also go into the in reaction. So these are the different types of the pericyclic reaction that we will discuss one by one. Here is a list of the key concepts that we are going to learn today. We will discuss first the types of the pericyclic reactions, which include the electrocyclic reactions. We will discuss some characteristics of the electrocyclic reactions, and then we will go into the mechanism of the electrocyclic reactions. Then we will study, if we have the time, then we will study the cyclo addition reactions, and finally we will discuss the sigmatropic rearrangements and the in reactions. So all it depends upon the availability of the time. So first of all, we will definitely today going to discuss the electrocyclic reactions, which is a type of the pericyclic reaction. So pericyclic reactions have four different types. First one is called the electrocyclic reaction, which is also called as the ring opening or the ring closing reaction. The second one is called the cyclo-addition reaction, and the third one is called the sigmatropic rearrangement, and the fourth one is called the in reaction. We will go into the discussion of each type of these pericyclic reactions one by one. A pericyclic reaction is a reaction in which bonds are formed and broken at the termini of one or more conjugated pi systems. If we talk about the classes of pericyclic reactions, as I have already informed you that the pericyclic reactions are of four different types. Electrocyclic reactions, also called as the ring opening and the ring closing reactions, cyclo-addition reactions, sigmatropic rearrangements, and the in reactions. Electrocyclic reaction is a type of pericyclic reaction in which it is an intramolecular reaction in which a new sigma bond is formed between the two ends of a conjugated or pi system. The product formed in the electrocyclic reaction is a cyclic compound which is always having one more ring and one fewer pi bond than the reactant. So here I have given the example of 1,3,5-hexatriene, which is having the 3 pi bonds. Upon electrocyclic reaction, it is converted into 1,3-cyclohexadiene, which is having the 2 bonds, whereas the reactant is having the 3 pi bonds. So the product in this case is having one less pi bond than the starting reactant, and the product is always a cyclic product. Here you may see that in the product a new sigma bond is formed, whereas in the reactant the pi bonds move in a circular fashion. On this slide I have mentioned or discussed some characteristics of the electrocyclic reactions. Electrocyclic reactions are always reversible. They move in the forward direction. The reactants are converted into the products, and the products are converted back into the reactants. In the reverse reaction, an electrocyclic reaction is one in which a sigma bond in a cyclic reactant breaks, forming a conjugated pi system that has one more pi bond than the cyclic reactant. So in the reverse reaction you will have one more pi system than the starting molecule. So here I have put the example of cyclobutene, which is having one pi bond, whereas the product is 1,3-butadiene, which is having the 2 pi bonds. So these electrocyclic reactions are always reversible. The second type of the pericyclic reaction that I have discussed in the earlier slide is the cyclo-addition reaction. In cyclo-addition reactions, two different pi bond containing molecules react to form a cyclic compound. Each of the reactants loses a pi bond, and the resulting cyclic product has two new sigma bonds and two less pi bonds than the sum of the pi bonds in the reactant. Here on this slide, I have given the example of the reaction between the ethene and 1,3-butadiene. When they undergo cyclo-addition reaction, a cyclohexene is formed. A cyclohexene has a cyclic structure, and you may see that in the case of the cyclohexene, two new sigma bonds are formed that I have highlighted with the help of two arrows, and you may also see a new pi bond which is formed when the pi electrons move in a circular fashion. The third type of pericyclic reactions are the sigmatropic rearrangement. In a sigmatropic rearrangement, a sigma bond is broken in the reactant and a new sigma bond is formed in the product. Hence, in sigmatropic rearrangement, pi bonds rearrange themselves. The number of the pi bonds does not change in the sigmatropic rearrangement, that is, the reactant and the product have the same number of pi bonds. In order to discuss the sigmatropic rearrangement, let us consider the example of 3-methyl-1,5-hexadiene, which upon sigmatropic rearrangement is converted into 1,5-heptadiene. In 1,5-heptadiene and 3-methyl-1,5-hexadiene, both have the total number of pi bonds equal to 2. So both have 2 pi bonds. So you may see that the number of the pi bonds remain conserved, and similarly in 1,5-heptadiene you may see a new sigma bond is formed that has been highlighted on this slide as well. As I have earlier informed you that in sigmatropic rearrangement a sigma bond of the reactant is broken. Which sigma bond of the reactant is broken in the sigmatropic rearrangements? The sigma bond that is broken can be either in the middle of a pi system or at the end of a pi system. The pi system consists of double bonded carbons and the carbon immediately adjacent to them. So here in the example of 1,3-hexadiene, which upon sigmatropic rearrangement is converted into 2,4-hexadiene, you may see that the one hydrogen atom that is bonded to the carbon atom with a sigma bond, it breaks its sigma bond and is shifted towards the other terminal of 1,3-hexadiene, and hence in this way, and additionally the pi bonds of the two pi bonds of the 1,3-hexadiene rearrange themselves, and hence in this way 1,3-hexadiene is converted into 2,4-hexadiene. So in this example you may see that both the sigma bond is being broken as well as the pi bonds are rearranging themselves. The fourth type of pericyclic reactions are the ene reaction. Ene reaction is a chemical reaction between an alkene and an allylic hydrogen, which is called the ene, and a compound containing a multiple bond that is called the enophile to form a new sigma bond with the migration of the ene double bond and 1,5 hydrogen shift. So the hydrogen shift, 1,5 hydrogen shift takes place in the ene reaction. The product is substituted alkene. The product of the ene reaction is always a substituted alkene with the double bond shifted to the allylic position. The ene reaction is always a 6-electron reaction. That is, the ene reaction always involves 6 electrons. In the ene reaction, two reactants are involved. One is called the ene, the other is called the enophile. The ene consists of a component that comprises of 4-electron system, whereas the enophile is actually a 2-electron component system. The 2-electron component is always a pi bond, whereas the 4-electron component consists of a pi bond and an allylic sigma bond. Here on this slide I have shown a classical example of ene reaction. It is a reaction between the ethene and propene. As a result of the ene reaction, these reactants are converted into the 1-pentene. So an ene may be an alkene, alkyne, allene, arene, or carbon heteroatom bond. Here on this slide I have summarized the 4 different types of the pericyclic reaction. What happens in these reactions I have shown on in the table number 1. In the electrocyclic reactions, one pi bond of the reactant is converted into a one new sigma bond, or one sigma bond is converted back into the one pi bond, since the electrocyclic reactions are the reversible reactions. Similarly, cyclo-addition reactions are also reversible reactions. In the cyclo-additions, two pi bonds of the reactants are converted into two new sigma bonds, or the two sigma bonds of the reactants are converted back into the two pi bonds, since the cyclo-addition reactions are also reversible. Similarly, the sigmatropic rearrangements, one sigma bond is converted into a new sigma bond, and in the imine reaction, one pi bond is converted into one sigma bond, and one sigma bond also migrates, and vice versa, since the imine reaction is also a reversible reaction. Notice that you might have noticed that the electrocyclic reactions and the sigmatropic rearrangements occur within a single pi system. So they are the intramolecular reactions. In contrast, the cyclo-addition reactions and the imine reaction involve the interaction of two different pi systems. That is, they are usually the intermolecular reactions. So you have to remember these differences between the electrocyclic, cyclo-addition, sigmatropic rearrangement, and the imine reactions. The four kinds of the pericyclic reactions share some common features which are discussed on this slide. These reactions, they are always concerted reactions, since they are the pericyclic reactions, and in my previous lectures I have discussed with you that the pericyclic reactions always follow the concerted mechanism. So all these four types of the pericyclic reactions follow the concerted mechanism. This means that what is meant by the concerted mechanism? This means that the bonds of the reactants are broken and the bonds of the product are formed in a single step or simultaneously. Therefore, there is one transition state and no intermediate. Because these reactions are concerted, they are highly stereoselective. What is the meaning of stereoselectivity? I will discuss in coming slides. These reactions are generally not affected by the catalyst or by the change in the solvent. So all the four types of the pericyclic reaction that I have discussed in my previous slides are usually unaffected by the amount of the catalyst or by the change in the solvents. The third type of pericyclic reactions are the sigmatropic rearrangement. In a sigmatropic rearrangement, a sigma bond is broken in the reactant and a new sigma bond is formed in the product. Hence, in sigmatropic rearrangement, pi bonds rearrange themselves. The number of the pi bonds does not change in the sigmatropic rearrangement, that is, the reactant and the product have the same number of pi bonds. In order to discuss the sigmatropic rearrangement, let us consider the example of 3-methyl-1,5-hexadiene, which upon sigmatropic rearrangement is converted into 1,5-heptadiene. In 1,5-heptadiene, and to explain the behavior of pericyclic reaction, in 1965, Woodward and Hoffman developed the conservation of orbital theory to explain the relationship among the structure and the configuration of the reactant. The relationship between the structure and the configuration of reactant, the conditions. Some pericyclic reactions proceed thermally, whereas some proceed photochemically. Why they proceed under thermal condition gave a particular type of configuration, whereas under photochemical reaction they give sometimes another configuration. So this behavior was explained in the conservation of orbital theory, which was developed by Woodward and Hoffman in 1965. The conservation of orbital symmetry theory states that in-phase orbitals overlap during the course of a pericyclic reaction. So what is meaning of in-phase? Mean the orbitals that undergo overlapping are overlapping to make the product must have same sign of their lobes that overlap with each other. The overlap of p atomic orbitals to form pi molecular orbital can be described by molecular orbital theory. The two lobes of a p orbital have opposite wave function signs. One is having the positive sign of a wave function, the other is having the negative sign of a wave function. that is the psi. These signs must not be confused with the charge of electron and the proton. When two in-phase atomic orbitals interact, a covalent bond is formed. When two out-of-phase atomic orbitals interact, a node is created between the two nuclei. Molecular orbital distribution of ethene. Ethene has one pi bond and it has the two atomic orbitals that combine to produce the two pi molecular orbitals. The in-phase interaction of the two p atomic orbitals gives a bonding molecular orbital designated by psi1. The bonding molecular orbital, this bonding molecular orbital is of lower energy than the isolated p atomic orbital. The out of phase interaction of the two p atomic orbitals gives an antibonding, that is the pi star molecular orbital, that is designated with the psi2, which is of higher energy than the p atomic orbitals. On this slide, I have shown the overlapping of the two p orbitals of the ethene. The p orbitals, the two p atomic orbitals of the ethene overlap in two different fashions. In one fashion, or in one way, they overlap in phase, and this overlapping results in the formation of a molecular orbital that is having the lower energy than the individual p atomic orbitals, and it is designated with the here I have designated it with the psi1, and it is called the bonding molecular orbital. Whereas in the other fashion, the two p orbitals overlap in such a way that the positive sign of the one lobe is in front of the negative sign of the other atomic p orbital, and this is called the out of phase overlapping. This out of phase overlapping generates an antibonding molecular orbital that is designated with the psi2, and it has one node. As the number of the nodes increases, the energy of the resulting molecular orbital increases, and hence we will say that the antibonding molecular orbital, which is having one node, has the higher energy than the bonding molecular orbital, and the energy of the atomic orbitals is intermediate of the energy of the molecular orbital and the antibonding molecular orbital. In the ground state, the two pi electrons of the ethene molecule will reside in the psi1, that is the bonding molecular orbital, and whereas in the excited state, the electrons will jump from the ground state into the excited state. Here on this slide, I have summarized the four different types of the pericyclic reaction. What happens in these reactions I have shown on in the table number 1. In the electrocyclic reactions, one pi bond of the reactant is converted into a one new sigma bond, or one sigma bond is converted back into the one pi bond, since the electrocyclic reactions are the reversible reactions. Similarly, cyclo reactions are also reversible reactions. In the cyclo additions, two pi bonds of the reactants are converted into two new sigma bonds, or the two sigma bonds of the reactants are converted back into the two pi bonds, since the cyclo addition reactions are also reversible. Similarly, the sigmatropic rearrangements, one sigma bond is converted into a new sigma bond, and in the imine reaction, one pi bond is converted into one sigma bond, and one sigma bond also migrates, and vice versa, since the imine reaction is also a reversible reaction. Notice that on this slide I have mentioned or discussed some characteristics of the electrocyclic reactions. Electrocyclic reactions are always reversible. They move in the forward direction, the reactants are converted into the products, and the products are converted back into the reactants. In the reverse reaction, an electrocyclic reaction is one in which a sigma bond in a cyclic reactant breaks, forming a conjugated pi system that has one more pi bond than the cyclic reactant. So in the reverse reaction, you will have one more pi system than the starting molecule. So here I have put the example of cyclobutene, which is having one pi bond, whereas the product is 1,3-butadiene, which is having the two pi bonds. So these electrocyclic reactions are always reversible. So as the energy of molecular orbital increases, the number of bonding interaction decreases and the number of nodes between the nuclei increases. For example, Psi1 has 4 bonding interaction and 0 nodes between the nuclei, and Psi2 has higher energy and then the Psi1 and has 2 bonding interaction and 1 node between the nuclei, whereas the Psi3 has the higher energy than the Psi1 and 2 and has 1 bonding interaction and 2 nodes between the nuclei, and the Psi4 has the highest energy among these 4 molecular bonding among these molecular orbitals and has the 0 bonding interaction and has the 3 nodes. So as the energy of the molecular orbital goes on increasing, the interaction between them goes on decreases, and the energy of and the number of nodes goes on increases. As the number of nodes increases, the energy of the molecular orbital also increases. So the thumb rule is a molecular orbital is bonding if the number of bonding interaction is greater than the number of nodes between the nuclei. And similarly, a molecular orbital is antibonding if the number of bonding interaction is less than the number of nodes between the nuclei. The normal electronic configuration of a molecule is known as the ground state. In the ground state of 1,3-butadiene, the highest occupied molecular orbital, that is HOMO, is Psi2 and the lowest unoccupied molecular orbital is Psi3. If a molecule absorbs light of the appropriate wavelength, the light will promote an electron from its ground state, the HOMO, to its LUMO, that is from Psi2 to Psi3. The molecule is then in the excited state. In the excited state, the HOMO is Psi3 and the LUMO is Psi4. So the answer to your small quiz is on this slide, and hopefully those students who will study this lecture will be able to answer my question, and those who will skip this lecture will definitely will not answer my question. Now let's go into the detail of the electrocyclic reaction. It's the appropriate time that we can discuss the electrocyclic reaction in detail. Now we have a sufficient knowledge about the pericyclic reaction. The cyclic compound is favored for electrocyclic reaction that forms 6-member ring, whereas the open chain compound is favored for the electrocyclic reaction that form 4-member rings because of the angle strain and the toroidal strain associated with the 4-member rings. Cyclobutenes are in electrocyclic equilibrium with 1,3-butadiene. So electrocyclic reactions are reversible reactions. So 1,3-butadiene will have a lower energy than the cyclobutenes, which are highly strained and will have the higher energy than the 1,3-butadiene, and it has therefore possible to convert the cyclobutane to butadiene thermally. So it is you can convert the cyclobutane into the butadiene by providing a thermal energy. The reverse reaction, the conversion of 1,3-butadiene to a cyclobutane, does not usually proceed under thermal conditions as it involves an ascending climb in the energy. However, there are some exceptions. The more the conjugated 1,3-butadienes it will absorb the light at longer wavelength than the cyclobutene, so it is possible to convert 1,3-butadiene to cyclobutene photochemically by choosing a wavelength at which the butadiene absorbs and the cyclobutene does not. For example, when cyclobutene substituted to cyclobutene, here shown on this slide, is provided the thermal energy, it is converted into 1,3-butadiene, and this 1,3-butadiene, upon providing the photonic energy, having the wavelength of the photons greater than the 210 nanometer, is converted back into the cyclobutene. So there are some exceptions to these rules. On this slide, I have mentioned or discussed some characteristics of the electrocyclic reactions. Electrocyclic reactions are always reversible. They move in the forward direction, the reactants are converted into the products, and the products are converted back into the reactants. In the reverse reaction, an electrocyclic reaction is one in which a sigma bond in a cyclic reactant breaks, forming a conjugated pi system that has one more pi bond than the cyclic reactant. So in the reverse reaction, you will have a one more pi system than the starting molecule. So here I have put the example of cyclobutene, which is having one pi bond, whereas the product is 1,3-butadiene, which is having the 2 pi bonds. So these electrocyclic reactions are always reversible. The second possibility for the head-to-head overlap of the two p orbitals is that one orbital rotates in the clockwise direction, whereas the other p orbital moves in the counterclockwise direction. And in this way, the two p orbitals become in front of each other and they overlap as shown on this slide, and this movement of the p orbital is called disrotatory. The mode of the ring closure depends on the symmetry of the HOMO of the compound undergoing ring closure. Only the symmetry of the highest occupied molecular orbitals, which is called the HOMO, is important in determining the course of the reaction, because this is where the highest energy electrons are residing. If the HOMO is symmetric, the end orbitals are identical. The rotation will have to be disrotatory to achieve in-phase overlap. So if your HOMO is symmetric, p orbitals will show disrotatory movement to achieve the in-phase overlap for the formation of a new sigma bond. Similarly, if the HOMO is asymmetric, rotation has to be conrotatory in order to achieve in-phase overlap. So here on this slide I have shown the disrotatory ring closure. Stereospecificity. A reaction in which the stereochemistry of the reactant controls the outcome of the reaction is called a stereospecific reaction, and this phenomena is called stereospecificity. When, for example, 2E4Z6E octatriene is given the thermal energy, it is converted into cis-5,6-dimethyl-1,3-cyclohexadiene. So the reactant undergoes an electrocyclic reaction under thermal conditions, and only the cis product is formed. So whenever you will heat the 2E4Z6E octatriene, you will always get a cis product and you will never get a trans product. This is hence under the thermal condition, this is a stereospecific reaction, because whenever you will change the configuration of the reactant, you will have a changed configuration product. So here the configuration of the product is changed, is controlled by the reactant. So it is a stereospecific reaction, because under specific reaction condition only a specific type of the product is obtained. So this is a stereospecific reaction. If you recall your previous semester, then E means the highest priority groups are on the opposite side of the double bond, and Z means the high priority groups are on the same side of the double bond. Ring closure of 2E4Z6E octatriene under thermal condition is disrotatory. So the p orbitals show disrotatory movement. The methyl groups are both pushed up or down, which result in the formation of the cis product. So here on this slide I have shown the disrotatory movement of the p orbitals of 2E4Z6E octatriene, and how from this octatriene cis 5,6-dimethyl-1,3-cyclohexadiene is formed. This is shown on this slide. You may see that when 2E4Z6Z after trying undergo an electrocyclic reaction under thermal condition, only a trans product is formed. So you may see that the electrocyclic reactions are highly stereospecific. So this is the example of stereospecificity of the electrocyclic reactions. The second possibility for the head-to-head overlap of the two p orbitals is that one orbital rotates in the clockwise direction, whereas the other p orbital moves in the counterclockwise direction. However, when the reactions are carried out under photochemical conditions, the products have opposite direction. For example, when 2E4Z6Z after trying undergo an electrocyclic reaction under photochemical reaction conditions, only the trans product is formed. So here you may see the photochemical conversion of 2E4Z6Z after trying into trans 5,6-dimethyl 1,3-cyclohexadiene. Stereospecificity. A reaction in which the stereochemistry of the reactant controls the outcome of the reaction is called a stereospecific reaction, and this phenomena is called stereospecificity. When, for example, 2E4Z6E octreotoluene is thermally if the reaction takes place under photochemical conditions, 2E4Z6Z octreotoluene undergoes counterrotatory ring closure, so both methyl groups are pushed down or up and the cis product is formed. So here on this slide you may see the photochemical conversion of the 2E4Z6Z octreotoluene into cis 5,6-dimethyl 1,3-cyclohexadiene. And here I have shown the counterrotatory movement of the p orbitals of 2E4Z6Z octreotoluene. Under the thermal conditions, 2E4Z hexadiene cyclizes to cis 3,4-dimethyl cyclobutadiene. Ring closure of 2E4Z hexadiene under thermal conditions forms cis 3,4-dimethyl cyclobutene, and the two p orbitals show counterrotatory movement. So here on this slide again I have shown the counterrotatory movement of the two p orbitals of the 2E4Z hexadiene. Under the thermal conditions, similarly 2E4Z hexadiene cyclizes to trans 3,4-dimethyl cyclobutene. Counterrotatory ring closure of 2E4Z hexadiene leads to the trans product formation. So here you may see that the two p orbitals are showing the counterrotatory movement in the case of 2E4Z hexadiene. The configuration of the product changes when the reaction is carried out under photochemical conditions. Under photochemical conditions, 2E4Z hexadiene cyclizes to give a trans isomer, that is, it produces trans 3,4-dimethyl cyclobutene. However, in contrast to the thermal condition, under photochemical condition, 2E4Z hexadiene cyclizes to cis product. So photochemical electrocyclic ring closure of 2E4Z24 hexadiene forms a cyclobutene with cis methyl group. So here you may see that both the one p orbitals of the 2E4Z24 hexadiene is moving the clockwise movement, whereas the other is showing the counterclockwise movement. So this is a disrotatory movement. Stereostatic reaction is a reaction where one stereoisomer of a product is formed predominantly because the reaction has a choice of pathways and one pathway is more favorable than the other. Consider the electrocyclic ring opening of trans 3,4-dimethyl cyclobutene under the thermal conditions as counterrotatory. Two products might be obtained from the counterrotatory ring opening allowed by the Woodward-Hoffman rules, but in fact only the trans product is obtained because there are severe steric interactions in the transition state leading to the cis product formation. The detail of the mechanism is shown in the coming slide. So on this slide you may see that the ring opening of the trans 3,4-dimethyl cyclobutane is stereoselective because the trans-trans isomer is stereoselectively obtained over the cis-cis isomer. If we summarize the stereochemistry of electrocyclic reaction, the stereochemistry of the electrocyclic reaction depends on the mode of the ring closure. The mode of the ring closure in turn depends on the number of the conjugated pi bonds in the reactant and the reaction condition, either the reaction proceeds thermally or photochemically. Electrocyclic reactions can be summarized by the selection rule known as the Woodward-Hoffman rules for electrocyclic reactions. A list of the books that you may read for further understanding of the pericyclic reactions. I personally like the book written by the Robert T.M. Obert, N.B. Organic Chemistry, Prentice Hall, New Jersey, 1992, 6th edition. So you may consult any of the books listed on this slide.